Good morning, everybody. So, this morning, what we're going to do is we're going to kind of talk about how populations change. We're going to talk about how the community and the populations exist and how ecology of all that ties together. So, first of all, chapter 6 is very has a lot of new information in it for you. So please make sure that you look at the TRG very thoroughly, and you might want to try to make flashcards of some of the terms. All right, so first thing we're going to do is we're going to kind of talk about how everything builds together. We know that everything is related to one another, but let's just quickly kind of refresh. So as we have individuals, then those individuals belong of a specific species, right? And that is dependent on how it undergoes natural selection and reproduces. Well, we then have a population of individuals. Populations of individuals, again, is of one species that exists together. They can exist constantly together, or it can be off and on. We'll talk about that later. Communities is when we have interactions amongst different species together. Ecosystems is, remember, the definition of all the biotic and abiotic factors in a location. So it encompasses communities, many different communities. And then we have the general biosphere, which is the entire globe and how we study the movement of, again, the biotic and abiotic factors here. So the air, the water, the heat, how it all moves. And we've studied that a little bit and will do so in the future. So first, let's define population ecology. So population ecology is everything, it's all those different factors that cause populations to grow or to shrink. So whether or not we're having an increase in births or immigration, notice the IM, immigration means incoming, or we have a decrease. Those would be our outputs, and that could be because of deaths, obviously, or immigration. EM means to leave, to immigrate. Immigrate, emigrate. You need to know that the letter N is going to be referencing population size within this chapter and the next. And population density is a very important concept, not only just to humans, but in ecosystems as a whole. If you think of humans, it's easy to think about population density because since we live in a city, our population density is higher. There's more of us in a given area than, let's say, if we lived way out in the country, in the sticks. Population distribution is how individuals are distributed with respect to one another. Again, you can kind of think of that in human terms as in we live rural, suburban, or urban. That's kind of an easy way to wrap your head around that. Population sex ratio is how many males to females there are, which when it comes to reproduction and trying to increase that population, that could be very important. Then we also have population age structure. This we will talk about in greater depth in chapter 7, but how many of different age groups are there? So are there a lot of elderly? Are there a lot of middle-aged? Are there a lot of juveniles? Infants? And again, I'm referring to humans, but this applies across ecosystems as a whole to all organisms. So there are different types of population distribution. We can have what we call nearly uniform. Everybody's pretty much spread apart. If you think COVID style, this would be social distancing. Everyone wants to kind of stay away from each other. Random. Random is just that. There doesn't seem to be an algorithm. There doesn't seem to be a mathematical sequence or logic to how that population may be distributed. And then there is also clumped. Clumped tends to occur within populations that prefer to work together in numbers, like schools of fish, or you can also think of like a grove of trees or something like that. Now, this is very important here. We have different things that influence the size of populations, and we have density-dependent factors and density independent. So let's kind of go over those. Density dependent factors are the ones where the size of the population it's influenced by different things, by different inputs. So these factors would include things like the availability for food, water, homes, like protection, nesting, nutrients. So those are density dependent factors. Without those items or enough of those, then you're going to have a decrease in populations because the health will suffer. There are also things called limiting resources. So a limiting resource is excuse me, it's a resource that if there's not enough, that there will be a overall decrease in population or not an increase. So as we were just talking about with the access to water or food availability, if that is not, if there's not enough to sustain the population, then obviously there's not enough to sustain reproduction and future growth of a population. There are also what we call those density independent factors. So these have no effect on how something is going to survive. So this would be random things. I usually tend to think of these as completely random 2020 type scenarios. No, I'm just kidding. But things like natural disasters are a great example of this. All right, now there are two growth models in this chapter. One is exponential. When you have something that is exponential, it increases at an enormously fast rate. And exponential growth rates tend to, they don't last forever because it's not sustainable. Something has to give. There's going to be a limiting resource that limits that growth, or there could be an external factor that would do so. But also, the exponential growth rate tends to occur more so when we have it tends to happen like early on in a community or a population boom. So here you'll see that over time we start to increase, but it increases faster and faster and faster and faster. This is highly density independent. And also, just think, this is under ideal conditions. If everything was perfect, we would have this J-shaped curve is the name that we give this. We will talk a little bit more about this together over Zoom and do an activity regarding this, but you need to know that an exponential growth model is not sustainable. It creates this J-shaped curve, and it's usually occurs early on in population booms because, again, it is not sustainable. Here is the formula for exponential growth. We will talk about this later. Pop, not poop. Okay, now, one thing I do want you to do is there's on page 206 of the new text, there is a do the math example. And I'm going to, on Google Classroom, kind of walk you through how to work this because you need to understand how to solve this. It's not that you need to know the formula per se to do an exact calculation. You need to identify the trends that you see with an exponential growth and to see like if it were kind of graphed out, oh dang, that's exponential. The other type is logistic. Logistic growth is more sustainable because what happens is you're going to have limits, whether it's those limiting factors that we talked about previously, or you're going to have a carrying capacity limit, meaning that you just can't you can't have more of that population live sustainably. All right. So sometimes it will grow until you hit absolute zero. So in a logistic growth model, here you can see we hit a zero growth rate up here at the peak. And this is what we call an S-shaped curve. We reach this carrying capacity, meaning that, and again, you need to know that this letter represents carrying capacity, capital K. Carrying capacity is basically the top limit of the population that can exist sustainably. And this is density dependent. So, like I said early on, a lot of times this early growth is exponential. It will start to slow naturally, and then it will start to really taper off. Logistic models can vary as well, and this occurs seasonally. It can occur based on migration patterns, reproduction in terms of if you think about how trees release their seeds or their acorns or whatever. So if you think about it, and then also if you have a natural disaster or food limits, food becomes scarce, water becomes scarce, habitat coverage does, then you could have a die-off. Numbers would start to increase back to the carrying capacity limit. Sometimes it'll kind of go over the top, right? Overshoot, and then start to kind of even back out. And this can waver back and forth until you reach that carrying capacity at a more constant rate. Okay, we're going to change gears here a little bit. So there are different reproductive strategies of organisms. We tend to call these either K-selected or R-selected. So I've talked about this briefly so far, but this is where we're going to talk about in a little greater depth. So K-selected species are ones that tend to they grow slowly until they really reach that carrying capacity. They tend to be higher up on the trophic cascade. They are higher up in that food chain. They tend to produce fewer offspring but care more or longer for those offspring. So examples of these would be things like elephants, whales, humans, other things that you see here in this picture. I relate K for kangaroo. That's an easy way for me to remember it because kangaroos are definitely not lower down on the food chain, and they have fewer offspring, care for them a long period of time. So it's kind of an easy way for me to tie that together. Then you have the other side where you have our R-selected species. These guys, they're kind of like you know what, we're just going to roll the dice, we're going to go for it. So our selected species are ones where that they tend to their populations grow very quickly because what they do is they have a lot of offspring at once, or a lot of offspring over a short period of time. So meaning that they might have very short gestation periods before they lay the eggs or give birth. But and typically too that these organisms mature very quickly. They don't have a lot of parental care. So these are those kinds of species where, their eggs are laid, the parents leave, and the babies are on their own. Like, see ya, wouldn't want to be ya, good luck. And so these are our selected species. I remember R for this because I either think of roach or rat. And to me, that just kind of makes sense, or rabbit. But because they have a lot of offspring, a lot of them also don't make it to adulthood, and a lot of them will perish before they reach maturity. So here are some a comparison between the K and R selected species. You do need to know this. Check your TRG for this. Okay, next. Survivorship curves. So in survivorship curves, this is an interesting model that we focus on in ecology, because there tends to be kind of three trends when it comes to survivorship. We have type 1, type 2, and type 3. So let me kind of explain what this means. So as age along this x-axis here increases, so here we have young, aging, maturing, old, death. What happens is I'll start with type 1. In type 1 organisms, we tend to have, we have this, let's say you were born, you were hatched, you sprout, right? And what happens here is as time progresses, you don't have a lot of death. You tend to survive fairly well, into long old life, and then you die off. Okay, so that's kind of type 1. Here it shows you an example of a whale. Type 3 is just the opposite. Type 3 is the ones where that you have a lot of offspring typically. Most of them do not live, do not sprout, do not hatch, do not exist beyond like an embryo or just being born, and therefore not very many mature, and as we move on, not many live into an old age. So type 3, think about it, that's a lot of your kind of what we call weeds. That could be also insects, organisms that have a very, very short lifespan typically, but their purpose is truly be born, reproduce, die. Then we kind of have this in between here. We have our type 2. So type 2, these guys, they kind of ride a fine line in between. They have a moderate number of offspring. They have a fairly good birth rate, survival rate through childhood or being a juvenile into adulthood, but it's pretty much a linear line all the way into death. So it's kind of an interesting phenomenon here where these organisms tend to be things like, think of like primary consumers, some secondary consumers, but things like squirrels, deer, birds. Most birds are type 2 survivorships. Okay, last slide, and then the rest is all on you. The last thing I want to talk about here is metapopulations. And this is actually like a whole area of study in ecology. We are barely touching on this, but metapopulations are it's an interesting thing because meta means many. And so what it is, it's different populations of organisms. So think about it, typically the same species, but they sometimes may come into contact with one another, sometimes more frequently than others. So, especially in terms of like migration, that's whenever their paths might cross, and that might allow for breeding to occur across the populations. So, but they tend to be a lot of times spatially distant from each other, whether it's because of a mountains or water, some kind of physical barrier may separate them. But if there's a migration period or something like that, that might bring them in together for a period of time, then that just might happen. So here you can see these are 3 technically different species, but notice it's S.O. lucida, S.O. occidentalis, S.O. Carunia. So these are subspecies of each other. So could they probably mate with each other and reproduce? Maybe. Okay. There may not be enough differentiation here yet where that they are distant enough in the genome where that they may not be able to reproduce. So that is the crash course for chapter 6. You also have the entire PowerPoint and your text and the AP Classroom videos that I would highly recommend that you look at if there's a topic in particular that you need to go over.